The same for a random variable y at the other location. Very, very simple. Two random variables, there we have them. All right. So I'm going to let I case and I control denote the sets of case and controls. We've got a whole set of cases on whom we have x, and a whole set of controls on whom we have x, and then similarly we have a whole set of cases and controls on whom we have y. All right. So we make minimal assumptions about the general population sample. In particular, I do not assume Hardy-Weinberg equilibrium, which would be another way of saying there's no quadratic term. All right, I don't assume that. And we'll see that more clearly in a minute. So, let mu and sigma squared be the mean and variance of x, and similarly we've got to use y and sigma squared y, and we've got a covariance between x and y, all right, which is basically like the correlation. So, all right, mu is like an allele frequency. Sigma squared is the variability, and well, we won't go. It's a bit like the Hardy-Weinberg disequilibrium, not quite. And the covariance is disequilibrium. That's all it's saying. So there's a parameter for Hardy-Weinberg disequilibrium is given by this thing. It's the probability somebody is AA minus the probability it would be if there were random mating. The two alleles A coming in together squared. Very simple. All right? That's the deviation for the Hardy-Weinberg deviation parameter. It can also be seen or shown that it's exactly half of sigma x squared minus the sigma squared of x given Hardy-Weinberg equilibrium. In other words, this parameter d is half the deviation of the variance from the variance expected if we had Hardy-Weinberg equilibrium. All right? If we had linearity, no quadratic term. That's what it is. All right? Now, the composite linkage disequilibrium parameter for L is A1 and B1 of markers A and B is given by this expression here. And what this expression is, it's the probability of being A1, B1 minus what it would be if they were independent. Probability of A1 times the probability of B1, okay? And that's 1/4 of the covariance. Let's see that. Let's see what we're talking about here. For those of you who are more genetically inclined, whoops, this one. These are the probabilities for what are known as unphased genotypes. For those of you who don't know what unphased is, don't worry about it. Just regular genotypes, okay? So what we have is, we have two of these things, all right? We've got the A marker. Whoops, wrong one. Now why is it not going back? I don't know. This one here. We have A1, 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 A2, A2, A2. This, by the way, is called a homozygote. This is a homozygote. This is called a heterozygote. Those of you statisticians think of the word heteroscedasticity, all different. All right? And here you've got the B, B1, B1. Those are homozygotes and the heterozygote. And what we have here is the probabilities of these. All right? The marginal probabilities. All right? All add up to 1. So if you are here, clearly all these individuals must have an A1 and a B1. These individuals, only half of them will have an A1 and a B1, because sometimes there'll be an A1 with an A2 or B1 with a B2. You know, there'll be an A1 with a B2 and an A2. Anyway, half of them, that's where this comes from. And these down here, they will have a 1/4 probability of being A1, B1. That's where all that comes from. So this is the probability of being A1, B1 minus the probability of this is the mean of the X and the mean of the B. That's that. Very simple, really, if you think about it. All right, so I've given you sort of a genetic way of thinking of it and a statistical way of thinking of it. All right. So you can jointly test the allele frequency and the Hardy-Weinberg disequilibrium contrast between case controls. And the null hypothesis is simply that this allele frequency is the same in cases as in controls, and simultaneously this deviation from Hardy-Weinberg equilibrium is the same as cases and controls. So you just test these two things. Now for a little bit of statistics, if I let, for the ith person, this be x and xi squared, the sample mean of this is sufficient for the allele frequency and the Hardy-Weinberg disequilibrium. All right? So then, when we go from that, we can see that this contrast, both together, can be performed by comparing this sufficient statistic for cases and this statistic for controls using Hertelling's t-squared statistic, and this test is given this way here, where this is the inverse of the variance matrix of these things, or at least this is the variance, and I've put here, this is the idea of this. So this is a vector of two things minus a vector of two things. Then you've got a vector here and here, and this is a 2 by 2 matrix. Here we're taking the generalized inverse. We'll do that in general, just in case the rank happens not to be 2 but 1. All right? So we take a generalized. So that's Hertelling's for doing two of these together. All right? And which is kind of thing people have been doing, I suppose. Now, if you add in this cross product, all right, for the ith person, you've got the same thing. This is the average of these as a sufficient statistic for the allele frequency A, allele frequency B, and what the geneticists call the disequilibrium, the correlation. All right? So, you can do it with another version of Hertelling's t-squared. Now you have a 3 by 3 instead of a 2 by 2. Just keep going. All right? So, you can also get the differences put in the LD contrast test, and you can do it given the allele frequency contrast. You can do all these various things. Okay? So, if you put all three together, so you would similarly, you take this thing, you'd have an x and a y, and if you put in the square terms and the cross product, and you can see if that basically the average of this is different between cases and controls with a similar test. All right. Let's look at this table. The idea of this table is we're going to use logistic regression. So, mu is going to be the probability of disease. All right? If what everybody would normally do, this is the logit of the probability of disease, rather than just probability of disease by its constant. And this is what one would be looking at, which corresponds in the linear model as opposed to the logit model. It corresponds, we're very close, the linear model to just the allele frequency difference, cases and controls. Right. This one has also, it's a 2 degree of freedom test because it's also putting in that quadratic bit, the dominance bit. All right. So here you might have the null hypothesis, that they're both equal to 0, here that 1 is equal to 0. This would have 2 degrees of freedom, have 1 degree of freedom. So those are the 2 single marker tests. Now you can have 2 marker association tests. Same kind of thing. You can put in 1 marker allele, other marker allele, the quadratic term for the other one, or dominance the other one, and you can put in this covariance. And this is the joint allelic Hardy-Weinberg disequilibrium and linkage disequilibrium contrast test. All those equal to 0. 5 degrees of freedom, and we call that 2-5. 2-4 is exactly the same, but we don't put in this term here. We put in we've got 2 of these markers. We put in the linear term and the quadratic term. We don't put in the correlation. That's what they're called the joint allelic Hardy-Weinberg disequilibrium test. Or you can actually put in these 2, just the additive bits, no quadratic bits, and their correlation. Joint allelic LD contrast test. And finally, you can do this one, which is the allele contrast at X and Y, these two different locations, additive. So you've got all these possibilities, all right? And by doing it in this format, logistic regression, which I still think people don't do very often. They go back to what the original was because that's the way it was done, though asymptotically they're the same. This makes it very flexible because you can test these in sequence or in other ways. So I want to show you that. You can use multi-stage tests. Now, there was this paper that was e-published and had this wonderful term in it. All right, the term was self-replication. And the idea of that is you use the same sample to replicate what you've already found. Now, I look in the published paper, they've taken away that word self-replication. I thought it was rather nice, using the same sample because you use different parts of the sample. Won't go into details. I feel so sorry. This was the one by Crystal Van Steen. All right, some of you may know that paper. It came out. And I swear, the e-published version had the word self-replication. Somebody must have objected and took it out. But it's lovely. You got this sample of pedigrees. You can do a test conditional on parental information. And you can also independently do a test on the parental information. So you're using the same sample to replicate. I thought it was one wonderful term. Anyway, the other thing you can do is you can do sequential tests. Do one at a time. For example, if you want, you can do this Hardy-Weinberg disequilibrium contrast test after adjusting for allele frequency information, which is used in the first stage. So in other words, is this significant given that one? We've got all this machinery that we can use in logistic regression. Now, this is where it gets rather interesting. Penetrance model and true marker association model. We have one, the model that we use for analyzing the data. The other, what's really going on. Right. So now we're going to have, we've talked about our two markers, now we're going to have a disease genotype. And it's been encoded this way. So we write the penetrance model in this way. And that is the probability of being affected, given you have the disease. Okay, it's going to have these parameters here, and that's if you're diseased, according to what this is the square of that. You'll notice that when this is squared, it's identical to this. Sort of interesting. And so what that boils down to is the following. These are constraints. And without going, because I think I want to get through this, I'm not going to let you just, the geneticists may ponder over this, and it is additive if this coefficient for d squared is 0. It's dominant or recessive according to whether that's plus or minus 1. And if this is 0, then that's a heterozygote advantage or disadvantage. You can go back to that previous table and work it all out. I'm not going to bother with that right now. So, given the true disease model and the structure, linkage to sequence structure, which is another way of saying, I know the correlations between these things, all right? We can set up the true single marker association model between the phenotype and single marker data. So there's the true model of what's going on. And then we can, with a lot of algebra,